Good evening. Today we are going to see Pascal's triangle. And Pascal's triangle we are using to decide the equation, or we can say that is displacement equation. So order of the polynomial, actually that is decided by using this Pascal's triangle. So now the selection of the order depends of the polynomial depends on the three things we have to check. One is completeness. Second, we have to go for compatibility. And third, we have to see geometric isotropy also. So these three things we have to consider to decide the order of the polynomial, and that geometric isotropy we can consider by using Pascal's triangle. The order of the polynomial approximation used for a given type of element. Now this is again most important. This is independent of the shape or size of the element. So order of the polynomial is not going to decide on your shape or size of the element. This ensures that the finite element model remains consistent and reliable across different geometries. The isotropy requirement, now you can see this requirement is constant strain for the linear order displacement function. Means constant strain and your displacement function is linear. Strain constant, displacement function is linear. The higher order polynomial functions considered shall be independent of the orientation of the local coordinate system. So this is again most important one. It is again independent of the local coordinate system. Now here we are saying constant strain and linear order, because if you will see, then you have u is equal to alpha naught plus alpha 1x plus alpha 2y. This is your linear displacement, because x proportional x to the power 1, y to the power 1. Now if we will go by d w by wx, which is my strain, and then in that case we will get first term becomes 0, second we will get alpha 1, and third again becomes 0. So your strain is constant, but your displacement is linear. The isotropy requirement, I already mentioned this, we have by using Pascal's triangles. For isotropy requirement, it is technique of including appropriate number of terms in the displacement. Means I can say that is coefficient. So we can have just, we have written over here, that is u is equal to alpha naught, alpha 1x, alpha 2. How many terms we have to include, that will be decided by using your Pascal's triangle. It also gives an idea about number of nodes. So that I am saying, and whatever number of nodes, that we have number of terms in the equation of displacement required for the completion of the selected polynomial. Now we can go with this Pascal's triangle. So in the two-dimensional problem, the term should not include from one of the axes. So now we have actually this Pascal's triangle, that is for 1D, we have for 2D, and we have for 3D. So this is clearly mentioned here. While we are considering two-dimensional problems, so we have to consider terms from two axes. And Pascal's triangles without means we have to consider, this is again important one, we have to consider the term using this axis of symmetry. So we are not in position, or we cannot select your terms from one side of the axis. We have to consider its counterpart of the other side or from the other axis. Now you can see this. I have drawn this Pascal's triangle for two-dimensional element. Our syllabus relates with 2 dimension. If you want, you can give third dimension. Means we can go like this: 1, then we have 2, and then we have 3, and then we have to connect likewise. So now here I have taken 2 axes only. So now we have 2D Pascal's triangle. So now you can see we have first this as 1, then we have, so this is, I can say, first node. Or I will first write, so we have 1, then we have x, y. So x to the power 1, y to the power 1. If we will go to the next, that is a parabola, then we have x square, we have x, y, we have y square. Means we are going to increase polynomial function of y and we are going to decrease polynomial function of x. So you can see this, I have x square y to the power 0, then I have x to the power 1, I have y to the power 1, and then we have x to the power 0, y to the power 2. So you can see we are going to decrease polynomial, power of polynomial x, that is from left to right, and we are going to increase of y from left to right. So likewise, if we will go x cube, then you can have this as x cube y to the power 0, then x square, y to the power 1, then x, y square, then x to the power 0, y to the power cube. So likewise, we are going to increase power of x from left, increase power of y from left to right, and decrease of x from left to right. And same that we have shown over here. So now you can see this. So here we have middle term also. When we will talk about x square y, alternately we have middle term in this one. If I will go to the x cube, then I do not have middle term, I have 4 terms. So alternately we have odd, even. First we have odd terms. If I will go to the second, then I have even term. So you can see this. So I have this as odd, then I have this as even, then again we have odd, even, likewise we have these terms. So now likewise we are going to consider these terms. So we have in this fashion. So now here we have 5 terms, then we have even 6 terms, and then we can have these 7 terms. So now while considering for 2-dimensional, we cannot consider terms only from one axis. We have to consider of this outer part also. What does it mean? Means when I will consider what is geometric isotropy, that means if I will consider x from here, I have to consider y. Now here, if I have 4, suppose I will consider a rectangular element. And in that case, I have this 4. 1, 2, 3, 4. Then I have this as first, then I have second, then I have third. Now I cannot consider x square because your geometry, isotropic geometry will not achieved. I cannot consider y square because again not achieved. Now I have to consider x, y because I have x and y both here. If I will consider x square, then that will be from one side axis. When I will consider x, y, then that will be satisfying my geometric isotropy, and that will be from both, considering both axes over here. X we have from x axis, y we have from y axis. So this will be my 4th term when I will consider 4-noded element. So likewise, we have to check is isotropic geometry satisfied, and that we can achieve by using this Pascal's triangle. Now you can see. So for one noded, so generally we do not have one noded element. So now it will start. We have 3 noded element. So we have like this. Means if I will write displacement function for this 3 noded, then I have this as u is equal to alpha 1, which is for this. Then I have alpha 2x, and then plus I have alpha 3y. So you can see this. We have x to the power 1, we have y to the power 1. So isotropic geometry is satisfied. So this is our CST element. Now we can have this 6-noded. So you can see this 6-noded. So if I will write function for this, then I have u is equal to, now 6 terms we have to consider: alpha 1 plus alpha 2x plus alpha 3y plus alpha 4x square plus alpha 5xy plus alpha 6y square. So you can say x to the power 1, y to the power 1. Here also x to the power 1, y to the power 1, x to the power 2, y to the power 2. So we have geometry maintained. This is LST element. So if we will go to this, then we have this as, now we are not going to consider 9 noded because we have 1, 2, 3, 4, 5, 6. So if I will consider 9, then 3 terms I have to consider. If I will consider x cube, y cube, and if I will take x square y, then your isotropic geometry will not achieve. Here I have x2, y1, but that term is not over there. Means likewise we do not have. So we have 10 noded elements. So you can see this QST, we have 10 noded because this isotropic geometry means now if I will write equation, I have u is equal to alpha 1, alpha 2x, alpha 3y. So this is 1, 1. Then I will get plus alpha cube, sorry, alpha 4 x square plus alpha 5xy plus alpha 6y square. Now you can say x square, then we have x1, y1, then we have y square. So this again we have according to our geometry, Pascal's triangle. Now plus, now I have alpha 7x cube. I have alpha 8y cube, means here we have 3, 3. Now I have to consider both these terms, x square y and xy square. One term I cannot consider, and therefore we will get it as alpha 9 x square y and alpha 10 xy square. And likewise, isotropic geometry we have to consider, and therefore QST element is not going to be 9 noded. To maintain isotropic geometry, we have to make it as 10 noded, and we have to give one internal node in this QST element. So likewise, we have to go for these Pascal's triangles to achieve isotropic geometry. Now, convergence requirement, we have 3 things we have seen. One is compatibility requirement, in which we have to see that adjacent elements do not have any gaps. This is most important when any gaps, overlaps, or discontinuities. That should not be over here. That care we have to take while we are going to consider any displacement model. That is most important. We have to keep in mind. So now you can see this, that is written here. So this we have, if we will go for axial members, so we have only axial displacement. So we have to check that compatibility requirement, that is only for axial displacement. But when we will go for flexural element, so flexural members, we have to consider both, that is displacement as well as slope continuity, and that is my compatibility requirement. So compatibility requirement, if I will say, then it is simply we have to ensure the continuity of the displacements. So that here in summary, that is clearly mentioned that the compatibility requirement for finite element model involves both displacement and slope continuity. In axial problems, only displacement, while in flexural problem, both the displacement and slope continuity. And considering this, we have to consider this displacement model. So that we have to ensure for compatibility requirement. Second, we have rigid body displacement. And in this, we have to actually, if we will see, then we have to see, do not have any discontinuities or gems. So here, all points must experience the same displacement. So if we will see your compatibility and then rigid body displacement, so when we are going to be continuous, so we have to see that in that continuity, all elements should experience the same displacement. And to achieve this, we are going to consider actually in our model one constant term. So you can see this, the constant term which is alpha 1, that we are going to consider which allows for rigid body displacement which ensures the overall motion of the structure is accurately represented. So to satisfy this requirement, we are going to consider a constant term in your shape function, or we can say in our displacement model. And third, already we have mentioned, for geometric isotropy, we are going to use Pascal's triangle. So these three requirements we have when we will consider any displacement model. One, we have compatibility requirement. Second, rigid body displacement. And third, we have that is geometric isotropy by using Pascal's triangles. So now we will stop here only. So remaining part we will see in the next lecture. Engineers Technical Hub, my my YouTube channel, that is Civil Engineers Technical Hub. Subscribe to it, and व्हिडिओ जर आवडला असेल तर नक्की लाईक करा. थँक्यू. नाव वी विल स्टॉप हिअर.